Welcome to this explainer. Today, we're embarking on a pretty incredible journey through the science of time travel, exploring the very fabric of space-time. We're going to strip away all that Hollywood fiction and uncover the actual, mind-bending reality of our universe. So let's dive right in.
We've got to start with the ultimate human question, right? It's the one that has captivated our imaginations for literally centuries. From ancient myths to classic sci-fi, we all have this deep psychological pull to master the clock. So, can we really travel through time? Is it a genuine scientific possibility, or are we just chasing an impossible dream?
To really wrap our heads around the sheer scale of this, let's start with a human perspective. In a very real way, you are already a time traveler just by looking up at the night sky. Seriously, looking at the starlight from the Andromeda Galaxy means we are looking 2 million years into the past, simply because that's exactly how long the light took to cross the cosmic void and reach our telescopes. When that light actually left Andromeda, humanity didn't even exist yet. Australopithecus was just taking its very first evolutionary steps. We are literally peering into the history of the cosmos every single night.
But, just looking at ancient starlight isn't exactly the physical time travel we dream about. To understand what's actually possible, we'll navigate this explainer through 3 distinct categories: confirmed physics, theoretical possibilities, and pure science fiction. Our foundation begins with Albert Einstein. Before his groundbreaking work, space and time were viewed as completely separate, rigid stages where the universe just sort of played out. Imagine the absolute shock to the scientific community when Einstein revealed that space and time are not separate at all. They're woven together into this unified, fluid, 4-dimensional fabric called space-time. They are fundamentally inseparable.
Einstein's brilliant work gave us 2 incredible theories for how we might actually manipulate time. First, we have special relativity, which tells us that moving at extreme speeds directly affects the flow of time. And then there's general relativity, where massive objects literally curve the fabric of spacetime using intense gravity, which also distorts time. To put that into everyday perspective, the GPS satellites orbiting our planet right now have to mathematically correct for both of these relativity equations constantly. If they didn't, the maps on our phones would drift by miles every single day. Let's look a little closer at how this builds into an extraordinary phenomenon called time dilation. If we place a highly sensitive clock on a really fast-moving spacecraft, it will actually tick slower compared to a clock sitting stationary on Earth. It's a fundamental law of our universe that these 2 metrics balance each other out. So basically, the faster you move through space, the slower you move through time. And this isn't just theory on a chalkboard. In 1971, the Hafele-Keating experiment literally proved forward time travel. Scientists synchronized incredibly precise atomic clocks, flew them twice around the world on regular commercial airplanes, and then brought them back to compare with the stationary clocks on the ground. The results were absolutely astounding. The flying clocks had genuinely aged fractions of a second less. We proved it! Forward time travel is an experimentally confirmed reality. To understand why this happens, imagine yourself as a stationary observer standing on a platform, watching Einstein's famous train analogy. A train rushes past you at incredible speed. Now, to a person inside that train, 2 lightning strikes hitting the front and back of the train might appear to happen at the exact same simultaneous moment. But to you, standing completely still outside, those lightning strikes will actually happen at different times. Because the speed of light is a universal constant, the passage of time absolutely has to be relative to the observer. There is no single universal clock ticking away for everyone. Having established that forward time travel is a reality, let's descend a bit deeper into the extremes of theoretical physics, black holes and cosmic gateways. So, theoretical physics allows for the mathematical existence of traversable wormholes. Imagine taking a flat piece of paper, drawing a line between 2 dots, and then simply folding the paper through higher dimensions so the 2 dots physically touch. That's a wormhole, a cosmic shortcut to the fabric of spacetime. If you went through this tunnel, you could emerge not just in a different place, but in a totally different era. But here's the massive catch. To keep that tunnel from collapsing and crushing you, it would require massive amounts of unstable, exotic negative energy. And frankly, we don't possess the technology or the understanding to harness anything like that. Black holes offer another incredibly dramatic theoretical gateway. Their immense gravitational forces warp the space-time grid so severely that time slows down to an absolute crawl for anyone nearing the event horizon. Think about the intense emotional weight of this reality.
If you were to orbit dangerously close to a supermassive black hole and then come back home, you could return to Earth finding that centuries have passed, and everyone you ever knew is gone. Meanwhile, you only experienced a long weekend in your ship.
But all of this brings us to the central, enduring mystery of our explainer today. If traveling to the future is perfectly compatible with relativity, why is traveling to the past so much harder? Why does the universe seem to actively push back against us going backward? To answer that, we have to cross the border into speculation and paradox, hitting the brick wall of the past. The very first major hurdle is this number right here, 186,000 miles per second, the speed of light. But listen, this is not just a speed limit for light rays, it is nature's fundamental speed limit for the transmission of information itself. Einstein's equations show us that you simply cannot reverse the time order of two events without exceeding this speed, and the fundamental laws of physics absolutely forbid that. We can actually visualize this rigid, forward flow using what's called a Minkowski space-time diagram. It sounds complicated, but in this graph, time runs vertically and space runs horizontally. An entire human life, from birth to death, is plotted simply as a single, unbudging line segment. It's a deterministic map where the past and future are already laid out on the page. We just cannot move backward on this line. Right now, the only way we traverse into the past is emotionally, through the traces of history left in old objects, photographs, and our own memories.
Traveling backward breaks the absolute foundational rule of a deterministic universe, which is known as causality. Causality simply dictates that a cause must always logically precede its effect. The glass falls and then it shatters. The universe demands a strict order of operations. If you somehow travel back in time, the effect, you arriving in the past, happens before the cause of you leaving the future. That shatters the entire logical framework of reality.
And violating causality leads directly to the ultimate headache for physicists, the grandfather paradox. Imagine successfully going back in time to prevent your own parents from meeting. Well, if they never meet, you are never born. But if you're never born, how on earth could you have possibly traveled back in time to stop them? It creates this inescapable logical loop that essentially forces reality to just throw its hands up in frustration. While physicists completely dread these paradoxes, they have proposed a few theoretical workarounds, though we are definitely bleeding into pure science fiction here. First is the Novikov principle, which suggests the timeline is fixed and self-correcting. Basically, whatever you do in the past was always meant to happen, so you can never truly change history. Alternatively, we have the branching timelines theory from quantum mechanics. That one argues that altering the past simply creates an infinite new parallel universe, safely leaving your original timeline perfectly intact. So where does this leave all our human dreams of stepping into a machine and witnessing history? Let's check out our final section, the limits of time machines.
Whenever brilliant mathematicians try to design a practical, physical time machine using the precise equations of general relativity, they inevitably hit fatal anomalies. They encounter things like a naked singularity, a devastating point in space where the laws of physics just completely break down and cease to make mathematical sense. When pushed to allow backward time travel, the universe digs in its heels and essentially cries out for help.
So bringing this whole explainer together, our journey brings us to this definitive conclusion. Number 1, forward time travel is an experimentally confirmed reality through extreme speed and time dilation. Number 2, traversing extreme gravity wells like black holes or wormholes is theoretically, mathematically possible but completely unproven and wildly dangerous. And number 3, practical machines capable of backward time travel currently remain purely science fiction. Time travel is such a beautiful, fascinating consequence of relativity and causality. But since a practical machine cannot rewrite the history we've already lived, we really have to accept the arrow of time. We are forever bound to the relentless march of the present. So, my ultimate question to you is this: without the ability to change the past, how will we choose to shape our unwritten future? Thank you so much for exploring the fabric of space-time with me.